So now that we know that there are trig functions, we should be looking at whether or not there are inverse trig functions. So let's start with our simplest and favorite trig function. Let's start with the sine function. I'm going to graph two periods of it on either side of 0, so negative 2 pi to 2 pi, and we know that its range is between negative 1 and 1 on the y-axis. So the domain of the sine function is negative infinity to positive infinity, because it goes on and on and on forever with no break. But the range is restricted between negative 1 and positive 1, unless, of course, the function is translated somehow by period or amplitude or some kind of a phase shift or something. Other than that, the standard position, this would be the sine function. So remember that an inverse function is a function that is reflected over the line y equals x. Same thing is true for an inverse trig function. Now, it looks as though in this region my graph coincides with the line y equals x. I'm going to have to ask you to use your imagination. There's a very small curve, and it is small, but a very small curve above that line on the upper portion and below that line on the lower portion. With my technology and human hand, I can't really sketch it as well as maybe a textbook picture would have it. So let's go ahead and write the inverse of this, or sketch the inverse. First thing to remember is that input values become output values. So where my x-axis contains negative 2 to pi over 2, now that's going to be my y-axis. Negative 2 pi to positive 2 pi. That's now my y-axis. And then the output values, 1, 2, 3, 4, 5, 6, are now my inputs. So this would be 1, and this would be negative 1. And I would go on, except I'm not going to need those other values. Now, if I were to sketch the function flipped over the line y equals x, I would end up with, well, let's see, the top curve, positive y and positive x. So positive x and positive y. So the top curve is going to go this way, and the bottom curve is going to go that way. All right, so this is the inverse of the sine function. Notice, sine may be a function, but the inverse sine is not a function. If I were to pass a vertical line test down this edge, I would intersect infinitely many times as the function goes on and on. So I'm going to have to make a restriction. And I would say that I'm going to choose, but that is so not true, because in mathematics, as we know, I don't get to write the rule book. It's already been written for me. We restrict the sine function between negative pi over 2 and positive pi over 2. That means I'm cutting off, we restrict the inverse sine function between negative pi over 2 and positive pi over 2. That would be like cutting the sine function off here and here. And so when I graph the inverse sine function, this is all I graph, this little green part. If I want to look at it on a unit circle, the only values I'm allowed to choose from would be the values are between negative 1 and 1, and the range will only give me output values between negative pi over 2 and pi over 2. So this is the range on the unit circle. So the domain for the sine function, for the inverse sine function, that's this function here, keeping the color consistent, the domain for the inverse sine function is, I shouldn't have labeled this. Hang on. Negative 1 to, that's pretty good on this side, to 1. I was pre-labeling, and then my drawing didn't meet the mark. So the domain of the inverse sine function is negative 1 to 1, inclusive. And the range, or the output, for the inverse sine function will be values between negative 2 pi over 2 and positive pi over 2. Now you might be asking, what do you need to know? What do you need to memorize? You will actually have to be able to, at least kind of in your head, flip this and know, if I said, which is the graph of the inverse sine function, you would need to know this portion of it. Negative pi over 2 to pi over 2, negative 1 to positive 1. That you would need to know. Now, of course, the translations work in exactly the same way as any other graph that we've done so far, both polynomials and trigonometric functions, but we're just not going to do those sorts of evaluations at this time. But you do need to know these 3 pieces of information about the sine function, and you should commit those to memory, or at least be able to put it together by retracing this idea. Let's do the same thing now with the cosine function. And I'm only going to do one period of the cosine function, 2 pi, 0, and then this is also 1 to negative 1. So putting together the inverse cosine function, same thing happens. My x-axis labels become my y-axis labels, and then my y-axis labels become my x-axis labels. And let's see if I can hit the target this time. So this is the positive part. So that means I'm going to go from 1 to pi over 2 up and back up like that. So the inverse function looks like this. Or I should say the inverse cosine function looks exactly like that. Now again, my inverse cosine function is no longer a function, so I'm going to have to create some restrictions. And the restrictions that we use are right here. So now we can see that this is a function if I restrict it to only that area. So again, for cosine, oh, but where is that? Well, halfway, right? So this is at pi. So on the unit circle, the domain for the cosine function remains negative 1 to positive 1, but the range on the cosine function falls between 0 and pi. So this is the range for the cosine function. So the domain for the inverse cosine function, this is the range for the inverse cosine function. This is the location of the inverse cosine function, and the restriction is the domain is negative 1 to 1, and the range is 0 to pi. All right, so we've looked at the inverse of the sine function and the inverse of the cosine function. Now let's look at the inverse of tangent. And we'll do exactly the same thing. I'm going to start by graphing one period of tangent. Remember, tangent is restricted by asymptotes at negative pi over 2 and at pi over 2. And if I graph the inverse then, which just means take my values on the x-axis and migrate them to the y-axis, and a value on the x-axis and y-axis in both cases is the asymptote, right? So the x-axis asymptotes become y-axis asymptotes. And if I graph just one period of tangent, what I find is there is no restriction on the domain. And that makes total sense. If there's a restriction on the domain for the tan function, then the inverse tan has no restriction on the domain. I think I called that the tangent just a minute ago. This is the inverse tangent function, and there is no restriction on the domain. But the range carries a restriction. It's held between negative pi over 2 and positive pi over 2. Now, the inverse functions also have inverse functions. Yikes! That is very confusing. So cosecant has an inverse function, cosecant has an inverse function, and cotangent have inverse functions. We are so not going to look at those. What's important is that you are able to discuss and sketch out the domain and the graph of the arctan. This is also inverse tan is called arctan. And discuss the domain and sketch out the graph of the secant, not very well sketched. I'm sorry, of the arcsecant, of the arc cosine, too much terminology, I'm telling you, too much terminology, and that you be able to identify the domain and range and sketch out the graph of the arc sine or the inverse sine. So let's use what we have to do an example. Find the value of the inverse cosine of negative root 2 over 2. So what we're really looking for is which angle has a cosine value of negative root 2 over 2. Well, if I draw a unit circle real quick, that only means I care about x value being negative root 2 over 2. Because in the unit circle, r is 1, cosine x over r, I only care about the x value. But there are two angles that will give me a x value. Oh, that's not what I want. Of root 2 over 2, or negative root 2 over 2. But because I'm talking about the inverse cosine, I have to be talking about this angle because it's the only one on the interval for the range of my inverse cosine function. And so I can say that the angle involved is 3 pi over 4. 45 degrees in the second quadrant, 3 pi over 4. So I think this is a good time to kind of use a little lingo and kind of clarify some stuff. When we talk about the cos inverse of negative root 2 over 2 equals 3 pi over 4, what we're actually saying is if the cosine of the angle 3 pi over 4 equals negative root 2 over 2, and we know it does, the cos of 3 pi over 4 is negative root 2 over 2, then the inverse cos, or the arc cos, another way to write that, of the value equals the angle that gave us that value. So this is just speaking in inverses, right? If we're looking for the cos of an angle giving us a value, then we're looking for the arc cos of the value giving us back the angle. Inverse, or just reversing the operation. Let's do another example, this time with sine. Let's do the sine inverse, or the inverse sine of 3. So we want to find the inverse sine of 3. That means what angle gives me an output of 3? Or specifically, which angle gives me a sine value of 3? I don't even have to go that far though, because check this out. Right here, this would be the domain of this sine value. This is saying that a domain element includes 3 in the set. But if I come back over here to my sine, inverse sine domain, I only have domain elements between -1 and 1 on the inverse sine graph. So this is impossible. So this function doesn't even exist. Okay, one more example, and then I think I'll put off compositions of trig functions for another lesson. So let's look for a tangent or an inverse tan of root 3. Now this one's a little bit trickier because I'm looking on the unit circle for a point that has a value of root 3, but we need coordinates, right? We need an x and a y. So let's remember that tangent of x equals sine x over cosine x. But we need this to be root 3 over 1. Remembering that the tangent function, when we're writing the tangent function as sine x over cosine x using the left-hand rule, we remember that that's root 3 over 2 and 1 over 2. Sine over cosine, the 2's cancel, leaving me the root 3. So I know that I'm looking for a point where y equals root 3 over 2 and x, the cosine value, equals 1/2. They're both positive, so there are two places where the function would be a positive root 3, and that's where they're either both positive or both negative. So I could look at 1/2 root 3 over 2, or I could look at negative 1/2 negative root 3 over 2. So let's look at the output. Oh, I didn't put my circle. I don't really need it, but I'm going to put it there just to be sure. So for the unit circle, for the range, for our inverse tan values, our outputs or our range are only negative pi over 2 to positive pi over 2. And in our problem, the only angle that fits that is this first angle here. So I know that the inverse tan of the square root of 3 equals the angle 60 degrees or pi over 3. Whew, that is enough of that. I am going to put compositions of trig functions on the next video.